Okay, so example 2. We're going to use a calculator for this one, but we're going to kind of answer the original quandary that we were posed with at the top. How to approximate sine of 1, and how accurate is that approximation going to be? So that's what question 2 says. It says to first find the 5th degree Mach polynomial for sine of x. So what does Mach mean? What's the center? 0. And polynomial means squiggles or equals? Squiggles. Good. So let's do that first. So we know the polynomial. Let's go ahead and say that sine of x can be approximated by, if it's a Maclaurin polynomial, you can call it m. And if it's a 5th degree, you can put subscript 5 if you want. You could also call it t sub 5 of x. You could call it t of x. You can call it m of x. You don't even have to have the subscript. But you could have it there. It's kind of nice to have it. And now we'll start listing terms. Sine is even or odd? Odd. So the first term is 1 or x? X. Good. And then they alternate. So then it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Did it say 5 terms or a 5th degree? 5th degree. So with 3 terms, we're done, right? So there's your 5th degree. Then use the polynomial to approximate sine of 1. So here we go. Right underneath there, we'll just plug in a 1 for x. Everywhere we see it. So sine of 1 is approximated by the Maclaurin polynomial at 1, which is 1 minus, it ends up being 1 over 6, right? 3 factorial is 3 times 2. And then plus 1 over 5 factorial, which I'll just leave it as 5 factorial. Now, we have a calculator, so let's go ahead and punch it in. If you want to punch it in, verify my work here. We got 1 minus 1/6, and then plus 1 divided by 5, math, probability 4. And we end up with this number equaling 0.841 if you truncate. Okay? I'll just add another number there because it's 666 after that. 666 after that. All right. So there you go, 0.8416. You have 5 decimal places. Oh, I didn't even read that. All right, so I guess I have to add one more, 6. Okay. If it did say to give 6 decimal places, I would round. That would be kind of the exception to my truncating philosophy. All right. So that's it for Part A. Part B, use your solution from Part A to find an interval in which sine of 1 can actually live. So to do that, we're going to have to find a bound for the error. We're going to have to find the remainder, the maximum bound for the remainder. So here's what we're going to do. We just use a 5th degree polynomial. So that's n equals 5. So I'm going to do the work right here where I can see it. We'll say then that the remainder are from the 5th degree Taylor polynomial or Maclaurin polynomial at 1 is going to be bounded by less than or equal to the absolute value of the n plus first derivative. If 5 is n, what's n plus 1? 6. Good. It's the 6th derivative at some z value all over 6 factorial times x minus c to the 6th power. Now, of course, our center is 0, so I'll just put minus 0, and we're approximating it at what? 1. So instead of x minus 0, we're going to go ahead and plug in our x directly. All right, so now all I have to do is figure out what the maximum value for this is. So let's go off to the side here and do a little bit of work. If our function, f of x, is sine of x, we're trying to maximize essentially the 5th derivative. The 5th derivative of that function on the interval from 0, which is our center, to 1, which is what we're trying to evaluate it at. Okay? Now, if we start taking derivatives to get to the 5th, you'll see that the first derivative is cosine, and the second derivative is negative sine, and you keep going all the way to the 5th. But, well, do we know what it's going to be? Let's go all the way there. We get negative cosine, and then the 4th derivative is back to sine, and then finally the 5th derivative is cosine. Now, if you look at the graph of cosine by itself, it's chala. It looks something like that. Here is x equals 0, and x equals 1. Well, this is pi, so x equals 1 is going to be right there. So what we're doing is looking for the maximum value on that interval, which is what? And we're looking for the absolute value of it. So if you look at the absolute value of the graph, you reflect it up. As it turns out, we actually have a value here. The left endpoint of the interval, since it's cosine, is 1. But even if it weren't, even if it were sine, sine would start like this. And this is pretty much what you're going to do anytime you have functions like sine or cosine. If you were looking from 0 to 1, the maximum value would be sine of 1 itself. Well, we don't know what sine of 1 is, do we? So I'm not going to use the right endpoint for the maximum value because the whole purpose of doing this is trying to approximate what? Sine of 1. So I'm not going to use sine of 1, the approximated number, for my maximum upper bound. But what do we know about all the graphs of sine and cosine? Over their entire domain, and not just restricted to 0 and 1, their maximum value is always what? Well, what's the y value? 1. Okay, it doesn't matter what the x value is. Sine and cosine are always going to be bounded by their amplitude, and so the maximum value is 1. So anytime it's a sine or cosine function, you can just always use 1 as the maximum error. In other words, the sixth derivative, the absolute value of the sixth derivative at some z value is always going to be less than or equal to 1. So you can let that equal m. And so what we can do is we can now substitute this. Let me kind of scoot this over here. We can now say that the sixth derivative is less than or equal to 1 over 6 factorial times 1 to the 6. And there you go. You have your answer. It's 1 over 6 factorial. So that's typically what we do for sine or cosine. Of course, if the amplitude were 2 or something or 3, then we would use the amplitude value for the maximum value. So 1 divided by 6 factorial is going to be a very small number. It is actually 0.0013. It says give 5 decimal. Let's give 5 decimal places. There's 1, 2, 3, and then we'll throw an 8 in there. So I'm going to store that as alpha A. All right, so then part B. It says we're still on part B. I'm just doing it up here. Now that we have the error, this is the maximum error. It's also called the remainder. It's also called Lagrange error bound. We know that our actual sum is going to be within that of our approximated value, which we found right here. So here's what we could say. We know that sine of 1 then is going to be less than or equal to 0.84166 plus 0.00138. And to get the lower bound, we'll say 0.84166. That almost sounds like the making of a 1980 song about some girl's phone number. But it doesn't flow as nicely. It's 8675309 0.84166. That's not going to work, dude. That's not even a phone number with a decimal. Oh, I use decimals instead of dashes. Like 237 dash 1260 question mark. That's my phone number. I like to use dots. You know people that do that. It's like a formatting thing. Yeah, it looks kind of nice. All right. So anyway. Yeah, nowadays, because I don't want you to call me, actually. Try them all. You'll get me eventually. I won't answer. The song nowadays would have to have the 3-digit area code, right? Because all numbers do now. So anyway, the song is definitely dated. All right, let me go ahead and figure out what this is. What? Oh, yeah, okay. Yeah, sometimes I forget I'm recording. Oh, well. I was going to say, I erased it now. You don't know what it is, but all you have to do is go back and pause it, and then write it down, and then give some trial and error. So I feel sorry for the other people with the same 6 digits. Oh, well. It'll go straight to voicemail, so I'm happy to disappoint you. All right, so... No, I don't even do that. No, I let it be that, like, it's the guy that came with the phone. You have reached 287-126 question mark. Leave a message, and then I never check it, so I never call you back. So anyway, we know if you want to get hold of me, you got to come to this room at 7 in the morning on a weekday where school's in session. Okay. Speaking of, remember, this Saturday, 7:30, another review in here, 7:30, dark and early. The we know that sine of 1 is going to be in between there. Now let's do the follow-up question. We'll actually figure out what sine of 1 is. Could sine of 1 equal 0.87? No. Comma, since 0.87 is not in the interval from part B. I'm not going to write all that out. Got it? Yes. All right. Could it equal, I'll make up another question. We'll call it part D. Could it equal 0.842? Yes. Yeah, it could, because that is in the interval. So for what it's worth, let's figure out what sine actually is. Make sure you're in radian mode. Type in sine of 1. Sine of 1, and we have this luxury now. Sine of 1 is actually equal to 0.8. 0. Is 8. It was almost the same. 0.841409848. Okay. Question mark. Yeah. Now 7098848. Okay. Is that number in our interval? It is. It is. And we also already know how the calculator gets that number, right? It is programmed to give you sine of 1 by using a polynomial approximation. That's how it does it. I don't know how many terms it uses, but you looked it up on Google, right? And Google is not like Wikipedia. You looked it up on Google? I remember. Y'all kind of look the same. Today. Yeah. It must use like a, I don't know, a 15th degree polynomial, let's say, because I'm pretty sure that it gives you accurate decimal places all the way out to the end of what it can display. And it does it pretty quickly. So yeah, there you go. But before calculators, computers where you could program things to do this was good enough for these people. Like, okay, sine of 1 is going to be somewhere in between there. And again, if they had picky wives, well, I want a smaller margin of error. It's like, golly, I guess I'm not doing anything this weekend. I'm going to be approximating sine of 1 to greater accuracy by using maybe a 7th degree polynomial. Okay? Wives are not always nagging like that. Guys need wives that take care of them. Without my wife, I would literally be dead. I would not be alive. Yeah. You can't live without it. No, well, she has saved my life literally several times. Yeah. Don't do that. Okay. All right. And I live another day. Yeah. Yeah. You have the idea down? So we had one where it was given to us, the maximum value. We had another one where we kind of had to find it. Let's look at, I'm going to jump past there and jump back here. Let's jump to example 5. Okay? Because we want to finish today. This was on the 2011 exam, an actual question, 6th question. Typically, it's the last question. It said, let f of x equal sine of x squared plus cosine of x. And you wait a little brief amount of time for anyone to object. And no one objects. And it's like, good, because you read the instructions. Just to let it happen. The graph of the absolute value of the 5th derivative is shown at the right. Ooh, ain't that a beaut. Okay? So it looked like maybe f of x, the 5th derivative, kind of dipped below, but remember the absolute value reflects it up. All right, yeah, I know. That's a real dry erase marker board. Write the first four non-zero terms of the Taylor series for sine of x centered at 0. And write the first four non-zero Taylor terms for sine of x squared about 0. Okay, so first things first, sine of x. Now, did it say polynomial or series? Series, okay. Did it say the general term? Does it say general term? No. Okay, good. So we won't volunteer it. So this is going to equals or squiggles for series? Equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus ... That's the difference with the series. You put equals, but you got to put plus ... No general terms, so we don't have to write it. And now the first four non-zero terms for sine of x squared. So now sine of x squared, all we have to do is substitute x with x squared. So I get x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial plus yada, yada, yada. Okay, good. Nice. Check, check. Questions on that? That was easy. That's easy, right? Everyone, that's easy? Yeah, yeah. It's easier than like trying to do this in the hallway with everybody. Because that did not work. Follow the leader was a lot harder than I thought it was going to be. Well, yeah, yeah. Yeah, but we recovered. Mrs. Bach took charge. When we were standing there, we were looking down the hall, and it was just like, every students were everywhere. It was like, and we were like, whoa. And your mom made eye contact with me like, whoa. And I went, whoa, what to do? And your mom just, boom, she went to the front, and just like herding cats, she had everyone back going in the right direction. So she saved the parade, and then we were able to finish. So. No, heck no, because I was in charge. I was gonna expand it. Yeah, we need more though. We need more. Okay. Yeah, more water stations along the way. All right. Letter B. Write the first 4 non-zero terms of the Taylor series for cosine at 0. Okay. First 4 non-zero terms. So cosine of x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus yada, yada, yada. There you go. Use this series and the series from sine of x squared to write the 4 non-zero terms for the Taylor series for f. Okay, so they're kind of setting you up for success. This is what you would do on your own. You would create the pieces, and then you would want to combine them. So here's what we're going to do. I would probably, if this were me on the actual test, I would probably rewrite this. You may not have to rewrite it because, of course, it's going to be right in front of you. But if you rewrite it again down here, now you kind of have it stacked. And so if you add these vertically, what is the left side going to become? What is cosine plus sine of x squared? What can we call it? F of x, yeah. So I'm just going to say f of x equals. And now I have to add like terms. So let's start with the smallest constant. It's 1. There's no other constant on the second row, so it's 1. But now I have like terms, right? Oh, goodness. Oh, yeah. I have 1 minus this. 2 factorial is really 2, right? So it's really 1 minus a half, which is positive a half. So it's positive x squared over 2. Yeah. And then I look for a cubic term. I don't have a cubic term, right? Do I have a 4th degree term? I do. And I just have one of them. So it's plus x to the 4th over 4 factorial. And then I don't have a 5th degree term. Do I have a 6th degree term? Yeah, I have 2 of them. So now, if I do that, here's what I'm going to do. I'm not going to take too much time messing around with it. I'm just going to say it's negative, and I'm going to factor out the x to the 6th. And now if I factor out the negative, I can use the coefficients 1 over 3 factorial and 1 over 6 factorial. 1 over 3 factorial plus 1 over 6 factorial. Or you could just say minus a third minus a 6th. But you do want to write them as a combined coefficient of x to the 6th because it's part of that term. And then, do we have 4 non-zero terms? Yeah, we have a constant, a squared term, a 4th degree term, and an x to the 6th. So you do need to somehow combine the coefficients for your 2x to the 6th. This was no calculator, so that would be fine if you didn't actually want to compute it. All right? Everyone okay with that? Well, you could, because I had a 1 on the bottom, and I had a minus 1 over 2 factorial. And because 2 factorial is easy to compute, it's just 2 times 1, which is 2. Rather than put it in terms of factorial form like I did on the 6th degree, I just said it was 1 minus 1/2. And 1 minus 1/2 is just 1/2. Okay? You're not going to lose anything if you want to put 2 factorial there, because 2 is the same as 2 factorial. But essentially I did this. I did 1 minus 1/2. Okay? So now we have f of x. Now it says to find the value of the 6th derivative of f at 0. How am I going to do that? We have f of x now. And remember, f, the 6th derivative of the function at 0, is partially related to the coefficient of the 6th degree term, right? So let's remember off to the side here. in general, the terms are the nth derivative at the center all over n factorial. These are the coefficients of every term. So if we want the sixth, I should put that in parentheses, if we want the value of the sixth derivative at 0, then the coefficient of the sixth degree term will be that over 6 factorial, right? Okay? That would be the coefficient of the sixth degree term. Well, we already know, as you said, what f of x is. So what is the coefficient of x to the sixth? That should equal negative 1 over 3 factorial plus 1 over 6 factorial. And so all we need to do then, if they're asking for this, they're asking for the numerator of the coefficient. So what we've done here is essentially we've reintroduced Taylor's theorem, and then we brought in the coefficient from our polynomial that we created, and we just equated the two. So if we solve for that, we just multiply both sides by 6 factorial, and you get the sixth derivative at 0 is equal to negative 6 factorial, I'll put it in front, times 1 over 3 factorial plus 1 over 6 factorial. And would you need to simplify that? No. It looks like there's a whole lot of excitement going on in that answer, right? Yeah. Now, if you distribute, it might turn out kind of nice. Let's distribute. You get negative 6 over 3 factorial minus 6 factorial over 6 factorial. So let's just see what that would be. Remember, 6 factorial is 6 times 5 times 4 times 3 factorial, right? So that first term becomes negative 6 times 5 times 4. Then your 3 factorials will divide out. And then 6 factorial over 6 factorial becomes minus 1. So that does turn out to be a relatively nice number, right? 30 times 4 is 120, so negative 121. Not that you'd have to do that, okay? But guess what most people are going to do? They're going to forget to multiply both sides by 6 factorial. They're going to say, oh, you want the sixth derivative at 0? And they're going to just use the coefficient of the sixth degree term. So remember, you always divide by the n factorial. What time do we get out of here? I'm like looking for 5 minutes. Okay, plenty of time. 7. Oh, even more time. Okay. Yeah. Sometimes talking about time takes time. It takes time to talk about time. Let P sub 4 of x be a fourth degree Taylor polynomial for f at 0. Let it be. All right. Using the information from the graph above, because we haven't used that graph yet, other than marveled at it, show above that this is less than 1 over 3,000. So they're always going to allude to what the error bound is. What do you notice about this right here that I highlighted? This is the absolute value of the polynomial evaluated at fourth minus the actual function at a fourth. This is what we called the error. This is the error or the remainder. And what we're trying to do is show that the error or the remainder is bounded by 1 over 3,000. That is, the actual error is not going to be any more than 1/3000. Okay, so we're going to have to use Lagrange error bound. So here they tell you that if you're going to use a fourth degree polynomial, then the remainder from using a fourth degree polynomial, let's keep it in terms of x for now. Let's write it as a variable function. We haven't done that yet. That is going to be less than or equal to the n plus first derivative. Well, if n is 4, what's 4 plus 1? 5. So that's going to be less than or equal to the absolute value of the fifth derivative at, we'll call that z, all over 5 factorial times x minus, what's our center? 0. Yeah, we used a Maclaurin up above. So 0 to the fifth power. Okay, so that's the function. Now, of course, x minus 0 is just what? X. Yeah, x minus 0 is just x. So I'm just going to call that x to the fifth. You don't always have to write it, but it's nice to kind of take inventory. Now, here's the deal. If I can find a maximum value for the absolute value of the fifth derivative on my interval from my x value here is 1/4, right? We're trying to evaluate it at 1/4. So x is equal to a fourth, and my center is 0. So if I can find the maximum value of the fifth derivative on the interval from 0, my center, to 1/4, where I'm trying to evaluate it, I can plug in a 1/4 to both sides and replace the absolute value of the fifth derivative with that value. So let's go to the graph. Here's x equals 0, and where's 1/4? Ooh, 1's out here, and notice they have it partitioned into 4 equal parts, so this would be 1/4. So here's where it gets a little squirrely. We're looking on this interval here. What is the maximum value of that function? What is the maximum y value of this function in that highlighted region? Well, it's going to be the y value out of 1/4, right? Do we know what that value is? No, it falls right in the middle of some funky intersection. So if I can't use that, do I want to go to the first smallest number that I can determine or to the first biggest number? If I go smaller, now I risk having an error that doesn't bound the actual error. Okay? So you want to go to the first number that's bigger, that is still as small as possible. Okay, so what would be that number? What's the first y value that we know that is a little bit bigger than this y value? 40. Okay, 40. I want to call it, man, I wish I could call it like 20. I wish I could call it like 35. But I don't know if it's 35. 40 is the first definitive value that is bigger, but not huge, right? I don't want to call it 80. 80 would work, but it gives you a meaningless interval. So 40 works here. All right, so I know that this is less than, this is less than or equal to 40. Would you agree? On that interval, this is less than 40. Any objections to that? So this is your smallest safe upper bound. So now I can say that the remainder, using a fourth degree polynomial at x equals 1/4, is less than or equal to 40 over 5 factorial times 1/4 to the 5th power. Okay, so I plugged in two things. I plugged in my 1/4 for x, and I replaced the absolute value of the 5th derivative with its maximum value of 40. And then show that it's less than 1 over 3,000. Well, guess what? I'm just going to do this. I'm just going to say that that's less than 1 over 3,000. Do I know it to be true? I trust the method, and I trust my ability to use the method correctly. So I'm not going to compute it by hand, but I will show you, if I type it in the calculator, 4 to the 5th. Oops, I'd have to divide by 4 to the 5th. This comes out to be 0.0003255. And 1 over 3,000 is my inequality is not working. There we go. 0.000333. See that? So is in fact 0.00032 smaller than 0.00033? It is. Okay. So on a non-calculator, you're going to just trust the method, and if it says to show it's less than 1 over 3,000, compute the error using Lagrange error bound, and then say it's less than 1 over 3,000. And it should be. If you've done it all correctly, it should be. And that's it. That's Lagrange error bound. It's what most students go like, oh, I don't get it. But hopefully you do. All right, tomorrow we will go over BCO1 in class, so make sure you have at least the multiple choice done. We're grading it for accuracy. Have a great volleyball tournament today.